Okay, in this last part of the practical example, we'll finalize the dataset. After we split up the original array into two, text data and numeric data, we cleaned and pre-processed each part separately. Both arrays contain numerical data right now, so we can stitch them back together. Of course, to do so, the two arrays must have compatible shapes. So let's check the shape attribute for the string dataset. For this part, we can either use the lone data variables or the checkpoint data equivalents. Both approaches are correct, but the latter approach is slightly safer since we may have accidentally altered the contents of the string dataset after storing it. Therefore, that's the one we'll be using. The output states that it's a 10,000 by 6 2D array. Similarly, let's find the shape of the numeric dataset. This one is a 10,000 by 11 matrix. So both datasets contain the same number of rows, which means we can stack them side by side. In a new cell, we'll call the horizontal stacking function, hstack, and plug in the two arrays as inputs. We'll put the numeric dataset before the strings array, because the former contains all the IDs in its first column. Fantastic! We can see all the numerical data on the left side of the matrix, and all the converted strings columns on the right side. To make sure we're reading the output correctly, we'll call it shape attribute. The stacked array has 10,000 rows and 17 columns, 11 from the numeric set, and another 6 from the string data set. The stacking function works as intended, so we'll store the output in a new variable called lone data. In the next cell, we'll quickly check if it contains the stacked array. Yes, it does. Superb! Let's combine the isNaN function and the sum method to determine how many missing values are left in the array. We expect to see a 0 since we took care of them earlier in the practical example. Nice! Of course, the combined dataset needs to have a header too, so let's use np concatenate to stitch the header arrays of the checkpoint numeric and checkpoint strings NPZs. It's crucial that we set checkpoint numeric as the input in the first position, since we stored the numeric dataset on the left side of the complete array. The output contains the names of all 17 columns of our new dataset, and we can store these in a variable called header full. Okay, before we add the column names on top of the complete dataset, we want to sort the array. Let me elaborate a bit. We're only working with a sample of the dataset, so it's good practice to arrange all the entries according to an index variable. In our case, this variable is ID. That means we want to rearrange the entire dataset according to the values of the first column. We can see what these look like, but this wouldn't be very insightful, would it? So instead, let's use the sort function to obtain a sorted version of these values. The first entry is 373,332, and the last one is over 68 million. Now, if we call argsort, we'll see the indices which sort the ID column. If we pass this output as an index of lone data, we'll get this sorted array. However, we still need to store these values. So we'll add lone data equals at the start of the line. Great. Since this doesn't produce any output, we can call the variable and examine its outputs. Everything seems all right. A second way to check this is by calling argsort again. The variable should already be sorted, so we expect to get 0, 1, 2, and so on. And the output matches our expectations. Let's move ahead. After we sorted the array, we can finally stack the header on top of it. To achieve this, we call the vertical stacking function, vstack. Then as inputs, we pass header full followed by lone data. This will ensure the header stays on top rather than on the bottom. Let's take a look at the output. We see the function automatically converted all the numbers to text again. That's because the stack requires a unified data type across all rows and columns. By default, the function selects the smallest data type, which can hold any of the elements within the array. In this case, that happens to be a Unicode value of up to 32 elements. It is an appropriate type for the information we currently have in the lone data variable. Of course, we also need to store these values. So let's set loan data equal to this output. Splendid! The last thing we want to do in Python is to save the cleaned and preprocessed version of the dataset into a new file. So we'll call the save.txt function. In it, within quotation marks, we'll select a name for the file we want to create, extension included. Let that be loan data preprocessed.csv. As a second argument, we add the dataset variable. Afterwards, we'll set the format to %s, which is short for strings. Lastly, we'll pass a comma as the delimiter and run the cell. Unsurprisingly, we see no output because the function stores the values in an external file rather than display them on screen. Before we wrap up, let's go to the directory of our current Python notebook and use Notepad++ to open the CSV file we just created. We see all the headers placed at the very top and the rest of the preprocessed data below that separated by commas. And that's how we've successfully managed to clean, preprocess, and prepare the dataset for further analysis. Now our data science team can take this dataset and create a credit risk model for estimating probability of default. Fantastic! We've reached the end of this practical example. By now, I'm pretty sure you have gained confidence using NumPy to preprocess a dataset before analyzing it. In the next part of the course, we will continue to examine the various ways we can use Python tools to prepare and examine a dataset. Thanks for watching.